All right, my name is Munich. My project has wound up with multiple names, but I think I'm going to go with dynamic RNA just because that's nice and efficient. But I think it's officially called Researching RNA Simulation with SimTK. Now, before I go into the description of the project itself, I think, because I don't know how many of you here are bio majors, if any, but some review might be a good idea. So what I'm working on simulating is RNA, which is ribonucleic acid, which is a key part of taking the blueprints in your cell's DNA and converting them into useful things. Anything from proteins to enzymes to cellular structures, what have you. RNA is built up of 4 molecules that you see here with different bases. Adenine, cytosine, guanine, and uracil. Uracil is kind of weird because it replaces thymine, which is actually found in DNA, and I'm not sure, and I don't know if there's really conclusive knowledge as to why that is. But the structure of the molecules are all the same, where you'll have a phosphate group, which you can see in orange, a ribose, which is a sugar, and your base, which is any of those 4 different chemical compounds. So I'm going to be a little divergent right now. I'm going to bring up a simulation as an example. I'm going to start one because it takes a little while for it to run, just so you can see what the software can do. So let's see. All right, so this is the starting state of simulation. It's actually just 2 proteins interacting. Because if I were to do just a string of RNA, it's actually not super interesting, at least not for a long time. So I'm going to let that run in the background. And I'll bring it back up when I'm done talking. And hopefully it'll show us something interesting. All right. Okay. All right. So anyway, so the software that I'm using to do the simulation is based off of software developed by this group from simtk.org. It's a multi-body dynamic simulation program that's used for pretty much anything that can be defined as a group of rigid bodies connected by joints with some sort of arbitrary constraint system, and you can define that in any sort of geometry or any sort of coordinate system that you want, and it'll still work. So there's 2 levels to the software API. There's SimBody, which is the basic level that allows you to do things like make a double pendulum or any sort of general rigid body mathematics. And then there's a more in-depth add-on library called MoleModel that allows you specifically to do molecular dynamic simulation. MoleModel is a really powerful tool because, unlike a lot of other molecular simulation tool sets, it makes really good simplifications. For instance, if you remember from some of the other molecules that we were showing, you see these rings. Those rings are very stable. They don't move a lot, so you can actually treat them as solid bodies. That way you can reduce the amount of free motion in the system, so you can take steps and you can solve without having to solve for many variables. For instance, in RNA, the only real degrees of freedom are between the phosphate group and a ribose group, or a ribose group and a base group. Just those 2 bonds there. They are just allowed to rotate like such. So what this project that I'm working on is a continuation of research done by Mohammed Persina. I don't know if any of you guys had him for dynamics. But anyways, what he's done is he's developed a method of making the simulation even more efficient by looking at a sort of a sliding window frame average of the motion of the different residues. And so if a joint isn't moving a whole lot, you can just say, well, it's not really doing a whole lot. We can lock it, remove that degree of freedom, and make the simulation a lot simpler, allowing it to go faster. But then if there's a locked joint, and it's experiencing stress that would be equivalent to a mechanical brake, you unlock it and allow it to move freely so that it can go through what it wants, so you can retain the accuracy that your system needs, so that you don't wind up having just one solid object. It's still able to move the way it needs to. So what my project goals are for the upcoming, I guess for the rest of the summer, is I'm going to first try and develop a fully atomistic model where instead of taking any shortcuts and locking any structures, I'm going to have to simulate every single individual atom and run it to conclusion, which will take a lot of time and be very resource intensive. But it theoretically should give me exactly what would happen. So that way we can have a truth model that we can compare all future simulations to. From there, I'm going to compare those results to the current output from the algorithm, and then after we see sort of what's going on there, if it's okay to move forward or if we need to refine it further. If we move forward, what we're going to do is currently the algorithm only allows for torsional movement between the different bodies, but in reality the joints can get the bonds can come closer or farther apart. They can bend or they can rotate. So it's currently not representative of what could really happen inside a cell. So that's my goal for this summer, is to make an efficient but accurate model for RNA, which will have a lot of interesting uses by anyone who's researching RNA folding or protein folding, and which has a lot of medical applications. So I'd like to thank Professor Casina, Professor Krishnamurthy, Shauna Sullivan, and RCOS. Any questions?
I can see it now.
Oh yeah, let's see how that's done.
And how many, so when you do the true simulation, how many objects will be there for you, approximately ballpark? 1,000, 10,000?
Well, what we wanted to do is we wanted to simulate 50 residues, so that's 1, 2, 3, 4, 5, 6, 7, 8, 14, 15.
You can give me the number.
So 26 times 50, so a lot. Quite a lot.
It's 1,300.
Yeah. So let's see what it's up to.
You're not seeing it.
Yeah. Alright, so Alright, so you can see sort of how the electrostatic forces have caused the molecules to sort of bunch up and come together. Instead of just being straight out lines, they're starting to actually have effects on each other. And the simulation is taking really large steps right now, just to sort of speed it up. If it was doing it as accurate as it could, well, it'd be going very, very slow, and nothing interesting would happen in that period of time. But yeah, so the visualizer and all of these elements are all part of the libraries that come in, so really there's very little that you need to do to get something like this working. You can just define a string of protein bases or RNA bases and just set up an environment for it to be in, and then it works.
So what laws affect the forces? So is there what is underlying physical or chemical or mathematical laws?
It's a combination of laws. It's basic force equals mass times acceleration, Newton's second law. It's electrostatic forces. There's also this whole force field system called Amber 99. I don't know a whole lot about it, but it's pretty much, it sort of looks at all of the atoms and sort of looks at where the electron shells will be in the molecule and how that will affect its attraction or repulsion to other atoms.
The reason I asked that question is, this is somewhat, if you go to the macroscopic scale, it becomes like a multi-body, you get orbital movement and so on, you can view that.
Yeah, I actually see.
So that becomes, there the laws of, you take some other law, so I was just wondering.
Let's see if I can, I had an old file that, let me kill that. That was just a simple two-body pendulum. which was the first program that I had done. Hold on one second.
That's okay. Yeah, I understand.
Okay.
So the reason I asked even that question is whether you could, this Milky Way at home is another big project which does the galaxy computation of whatever this, using the
theoretically, you could use this software for it, but it's not really designed for it because this software is really good at looking at connected bodies and how they interact, not separate bodies. So.
I know I'd asked you about this a while ago, and I don't think you were able to advance over time. Is this multi-threaded?
Yes, it's highly multi-threaded. It's very hardware optimized.
So when you were running that on your computer there, is that entirely the CPU, or is it using the GPU as well?
It's GPU accelerated.
Okay. And that works on both NVIDIA and AMD?
Yep. It auto-detects your hardware and sets it up for you, which is really nice.
So once your prisms are folded, are you allowing them to write the lineage and show the difference in the structure before and after, or is it just showing the already folding after?
You can set it up to record whatever sort of data you want. You can save the positions of different parts of it by just adding a listener pretty much. You can have it record whatever information you want. In fact, you can set it up so that every frame that you just saw being printed out, you can have it save all of those, and you can then turn that into like a GIF file later on. So you can have a movie of what just happened. I'm not really focusing on protein folding because that's actually other area of research that's also being intensely studied that is similar, but it's slightly divergent from what I'm doing. But yeah, you can save your structures. There's a format, I think it's called PBD or something like that.
Yes.
Yeah, it's like a cloud coordinate thing that I'm not really familiar with.
I just want to know what database system behind is used for the simulation program.
Oh, it's C++. It's just C++ libraries that run in Visual Studio.
Not like any of database management systems like MySQL or something like that.
Not as far as I know. I haven't really gotten into the guts of it because it's really high level. And every time I try to really start investigating where things are coming from, it's turning out that a lot of stuff is hidden in pre-compiled binaries. So I can't really see what's going on. So it might be, but not to my knowledge.
Does your program, or does this program, allow for variables of temperature?
Yeah. It's that's one of the big things with it is that you can start at a lower temperature and allow it to increase. A chemical and its reactivity and its motion obviously is going to be highly affected by temperature. So there's ways to add thermometers to control the temperature or to just see what the temperature changes are.
So it can throw off the data from an exothermic or an endothermic reaction, tell you what the temperature change was for the...
I don't think it can actually do chemical reactions. It can't dynamically change bonding as far as I know.
Okay.
You might be able to do it. That's way away from what I'm doing. But it's possible, and that could be another project in the SimTK group, which is a really large group of researchers and clinicians and all sorts of people who are just